Okay, chapter 2 is really where the calculus begins. Chapter 1 was all the review stuff, and in section 2.1, they kind of introduced the idea of calculus, kind of a preview to calculus, by showing you some classic examples, okay? And specifically, we're going to introduce the idea of limits here, okay? Chapter 2 is really all about limits. And that's going to be the first of three major topics that we're going to be talking about in calculus, in Calc 1. Okay. Now, the tangent line problem is a classic problem to introduce this idea of limits. Okay. Now, the word tangent is Latin for the word touching. So when we talk about a tangent to a curve, we're talking about a line that is touching a curve. More specifically, it's going to be a line that is touching the curve at a single point, and a tangent line should always have the same direction as the curve at the point of contact. Because I can draw a line anywhere, okay? But if we take a look at an example here, suppose that we want to find an equation of the tangent line to the parabola y = x squared at the point 1, 1. And I'll call that point P. Well, so I've drawn the square function y = x squared, and I've labeled point P, which is on the parabola, and I've drawn a tangent line. Now, a tangent line, again, is a specific line that is touching the curve at a single point and also flowing in the same direction as the curve at the point of contact. Again, I could draw a line anywhere. You know, I could draw a horizontal line. I could draw a line slanted anyway. Okay, this is a specific line, and we want to find the equation of this line. Okay, some observations first. So we can find the equation as soon as we know the slope, right? Because I know a point on the line. Once I know the slope, I can then use the point-slope formula. The only problem is that I only know one point on this line, and I need 2 points to compute a slope. Okay. Now, because I don't have 2 points available on this line, what I'm going to do next is I'm going to approximate the slope of this line by selecting another point on the parabola, which I'm going to call point Q. Now, for what we're going to do next to make sense, point P and point Q are going to be close together. Okay, keep that in mind. Point Q is very near point P. Now, point Q is going to have coordinates x, y. Point Q is on the parabola, and y is equal to x squared. Okay, so point Q is going to have coordinates x squared. Now, I've drawn a line passing through points P and Q. This is not the tangent line. Okay, the tangent line only intersects the curve at a single point, also facing the curve and flowing in the same direction as the curve at the end, touching at a single point. But this other line that I've drawn is called a secant line. Okay, now a secant line is a line that's going to intersect a curve at 2 points. Okay, now if we keep in mind that points P and Q are very close to each other, then ideally the secant line is going to look very much like the tangent line. And if I allow point Q to get closer and closer to point P, I'll be able to have a better idea of the slope of the tangent line. Okay, now here's some notational stuff. M sub PQ, I'm going to let that be the slope of the secant line. Now that I have 2 points on this line, I can use the formula for slope. Change in y over change in x. So x squared minus 1 is the difference in the y values. Divide that by the difference in the x values. That's x minus 1. Okay, so M sub PQ, again, that's what I'm calling the slope of the secant line. Now, the slope of the tangent line, I'm just going to call that M. And again, once we know M, we can then get the equation, which is what the question is asking us to do here, find the equation of this tangent line. Now, if point Q is close to point P, like for example, what if point Q had coordinates 1.5, 2.25? Okay, like if x is 1.5, if you square 3 halves, that'd be 9 over 4. 9 over 4 in decimal form would be 2.25. Okay, like what if point Q was located at that spot? Well, then the slope of that line passing through points P and Q would be where you take 2.25 minus 1 divided by 1.5 minus 1. Change in x, change in y over change in x. Simplify that, and you should be getting 2.5 then as the slope of this line, okay, if x is 1.5. Now the next thing I'm going to do is I'm going to choose values of x close to 1. Now I can't choose 1 though, okay, because I know I can't divide by 0. That's a problem with x being 1. Okay, but I'm going to select values that are close to 1. And, you know, on either side here also. Okay, so I've made a table, and here's for when x is bigger than 1. And I'm going to plug those numbers into my formula here that I've created for the slope of the secant line. And then I'll do the same where I'm selecting values of x that are less than 1 but close to 1. So like for example, if x is 2, and we plug that in here, 2 squared is 4, minus 1 is 3, divided by 1 is 3. If x is 1.5, I've already done that, the slope of the secant line is 2.5. Okay. If x is 1.1, and you plug that into this formula here, you should be getting 2.1. Okay, now I'm getting closer and closer to 1, but on the right side of 1. So 1.01 would be closer to 1 than 1.1. Okay, if x is 1.01 and you plug that in here, you should be getting 2.01. If x is 1.001 and you plug that into this formula, you should be getting 2.001. Okay, now how about on the left side of 1? Let's choose values of x that are less than 1 but close to 1. Like if x is 0, negative 1 over negative 1 is 1. Okay, what if x is 0.5? Plug that in here. You should be getting 1.5. Okay, I'm going to get closer to 1, but on the left. What if x is 0.9? 1.9 would be the slope of that line then if x is 0.9. What if x is 0.99? Okay, the slope of the secant line then would be 1.99. And if x is 0.999, the slope of the secant line is 1.999. Okay, and so now from this table, it appears that the closer that x is to 1 on either side, the closer that the slope of the secant line is to 2. From our calculations, then, this would suggest that the slope of the tangent line is 2. Okay, now that's just a guess, I'm just based on what we see here. But it would be reasonable to say we think that the slope of the tangent line is 2. Now we say that the slopes of the slope of the tangent line is the limit of the slopes of the secant lines. And for notation, here's what we write down. The way that we read this is to say the limit as point Q approaches point P of the slope of the secant line. Well, that limit of the slope of the secant line is the slope of the tangent line, M. Okay, now we have a formula for M sub PQ. That's what we created up here. So if I were to write down this limit in terms of x, since I was selecting values of x in the chart that were, close to 1 here, so if I said the limit as x approaches 1 of the slope of the secant line, which is x squared minus 1 over x minus 1, that formula that we've been using, that is the slope of the tangent line. And we think that slope is 2. Assuming that the slope of the tangent line is 2, because that's just a guess, okay, Then using the point slope equation for a line, we're going to have this equation here. So y minus y1 equals the slope times x minus x1. Now, point P is on this line here, that is the tangent line. And so x1 is 1, y1 is 1. Okay, y minus 1 would be equal to the slope, which we think is 2, times x minus x1 is 1. Usually when we're doing things with equations of lines, and this is going to be how the book will want it also, give your answer in slope-intercept form. Okay, so y equal mx plus b. Well, if you distribute 2 and then add 1 to both sides, it looks like y is equal to 2x minus 1 would be the equation of this line here in the problem. Okay, now here's an illustration of the limit process that we just used. Okay, I want to emphasize that for our calculations here to make sense, point Q has to be close to point P. Okay, if point Q is way out yonder, then this line here is going to look nothing like this line here. Okay, so keep that in mind. Point Q is close to point P. Now in this chart, x was getting closer and closer to 1 on either side. Okay, so as x is getting closer and closer to 1, point Q is going to get closer and closer to point P, and the secant line is going to look very much like the tangent line. Now it's not going to be the tangent line, okay, since point P and point Q are two different points, okay, but the closer that point Q is to point P, like we can have at least an idea of what that tangent line equation would be here. All right. Another classic example that I wanted to leave you guys as a reading assignment is called the velocity problem. That's on page 80. It's example 3. I was just kind of highlight that real quick here. On the previous page, we just looked at the tangent problem, and here's this should look familiar. I've just gone over that tangent line problem. Okay, and if you go to the next page, then here's the velocity problem. Okay, that's example 3. Now the velocity of a car, let's say, the speed of a car is changing. If you drive your car somewhere, the speed is going to vary, during that route, wherever you're going. Okay. Suppose that a ball is dropped from the observation deck of the CN Tower, which is located in Toronto, and that's one of the buildings that has one of the highest observation decks in the world. You're 450 meters above the ground, okay, and we want to find the velocity of the ball after 5 seconds. Well, let's see, that would be kind of a difficult problem to know. If you were to drop a ball off the top of the building, and of course the ball is going to speed up as it's approaching Earth, right, due to gravity. And suppose that we wanted to know the velocity of the ball at a single moment in time, which is 5 seconds here. Okay, well that would be kind of tough if somebody were to essentially take a snapshot of a ball next to a building and then ask you how fast is the ball going. Well, that'd be tough to tell. Okay, it would be a lot easier if we had like a video rolling. Okay, and that's what they're describing here. Like, what if you had a video photographing the ball as it's falling down, approaching Earth? Okay, and what if you were to able to calculate the average velocity over a given time span? Okay, now that is something that we could be able to calculate, and they're describing that formula here, how to get the average velocity over a given time span. You're going to use the change in position over the time elapsed. Okay, so like what if I were to, I could very easily find the speed of the ball as it's going from 5 seconds to 6 seconds. Okay, and then I'd want to shrink that interval. Like what if we wanted to know the speed of the ball from 5 seconds to 5.1 seconds? Or 5 seconds to 5.05 seconds? Or 5 seconds to 5.01 seconds? You know, I'm getting closer and closer to 5. I'm shrinking that video length, but I'm still able to calculate an average velocity. Okay, well, the shorter the video length, like the better idea I'll have of what's called the instantaneous velocity. Okay, that's the velocity at a single moment in time, which, you know, we want to know the velocity of the ball at exactly 5 seconds. Okay, well, we say that the instantaneous velocity is defined to be the limit of the average velocities. Okay, and from this table here in this particular problem, it looks like the velocity of the ball at 5 seconds appears to be maybe 49 meters per second. You know, really, it looks like that's where the numbers are headed towards in this chart here. Okay, and so that would be our guess. The velocity is 49 meters per second. Okay, now that's a guess. You know, it might not be 49 meters per second. Okay, it might be 49.00000, you know, 28 meters per second. Okay, so keep that in mind. You know, it's just a guess. I'll talk about guessing limits here. That's not really an efficient method, okay, but it's somewhere to start, okay. And yeah, but this problem is essentially the tangent line problem. In fact, they describe that here, okay. I said that the instantaneous velocity is defined to be the limit of the average velocities. Okay, well, that's exactly what we were doing in the tangent line problem, right? The slope of the tangent line is the limit of the slope of the secant lines. Okay, you have 2 points where one is getting closer and closer to the other. Okay, so you're shrinking the length, well, that's exactly what I'm doing here, right? I'm shrinking the length of this interval. And that allows me to have a better idea of what the velocity would be at a single moment in time. Okay, just like by shrinking this distance, that allows me to have a better idea of what the slope of the tangent line is. That is the slope of this line as a single point. Okay. So I'd like you to read that over. You know, it's a quick read, just a little bit more than a page there. Okay, and I've kind of summarized most of what we need to know already. So just a little introduction there. And of course, we'll look at all the, you know, classic examples as we go along. Another classic example is the area problem. Okay, when you go through a calc class, there's really 3 major topics that you're going to study. Okay, and we're introducing one of the 3 major topics right now, which is the idea of a limit. Okay, the next major topic that we're going to talk about is derivatives. And then the last one is integration. Okay, and so I have a lot to say about that. That's, you know, we're looking at a whole semester course here, so we're gonna focus on limits here at the moment in chapter 2, and so I'll go ahead and stop the video right now.